Alright, hello again everyone. Today I'm going to talk again about binary relativity, and I'm going to explain what the factors are, the changing conditions in binary relativity. I'm going to explain how we will be able to prove binary relativity, and I'm going to explain some of the evidence we already have for binary relativity. Alright, so first I'll go over the equation again, and with some additions. So, okay, gravitational energy being equal to mass times the speed of rotation squared. Now the triangles in math mean change. So a change in gravitational energy is directly proportional to a change in mass or a change in the speed of rotation. And in the denominator, the change in velocity means that basically the more velocity you have in an object that has gravitational energy, the less gravity it has. So the faster an object goes, the less gravitational energy. And c squared, it might be possible that the speed of light changes over time, and I might do a different video explaining a theory which could explain a change in the speed of light. But that's more speculation than the rest of this. Alright, so binary relativity. Out in the universe, the evidence for it is really has mostly to do with galaxies and black holes out in the universe. So, okay, most galaxies, spiral galaxies in particular, have flat rotational curves, which means that the further you go out from the center of a galaxy, from the galactic center, then basically the speed of rotation, the further you go out away from the center, is higher than scientists think it should be. Now this gets explained naturally with the gravitational energy because it's mass times the speed of rotation squared, so that when you have a black hole, say, driving, basically being the engine for a galaxy, if the rotation, there's a flat rotational curve because of the gravitational energy that drives it. So that perfectly fits in with the model. And that's a big chunk of evidence right there for gravitational energy. Now, how to prove binary relativity really has to do with there's actually a lot of ways to do it, but one of the ways is to basically observe a spiral rotating galaxy versus a non-rotating galaxy, like an elliptical galaxy, and to observe the starlight behind those two galaxies, ideally with the same mass, so that the light behind a rotating high mass galaxy will be bent more than the light of an equally mass non-rotating galaxy, which will prove that a gravitational energy is stronger than basically just the gravity alone of a non-rotating galaxy. Basically proving that a gravitational energy is valid, and that's equal to mass and the speed of rotation squared. So also, how we can prove the denominator is by observing light being absorbed by black holes. Now, that might be a little harder to do, but we already know that light gets absorbed by black holes, but I'm not sure if we've observed a light beam actually being absorbed. Now that'll prove that a black hole operates faster than light, but also is more powerful than light. So the more mass and rotational energy you have in a black hole, the more light and energy it can absorb. And those are two big ways to prove it. Now another simpler way to prove just the gravitational energy portion is that, let's say you had a rotating helicopter blade in outer space, though. Now instead of it creating a lift in outer space, it's going to create gravitational energy. So that matter will be absorbed from both sides of a rotating helicopter blade, coalescing basically more or less to the helicopter blade until it picks up enough energy to break the orbit of that rotating helicopter blade. So that's a simple way to prove binary relativity. Gravitational energy being equal to mass times the speed of rotation squared. And that's pretty straightforward, and that's a simple experiment for us to conduct. And really the hard part is convincing people like NASA to send up a helicopter blade or a small version of that to test this hypothesis, this theory of binary relativity. So in time, I'm sure that people will want to verify this because it's provable. And yeah, that's the most simplest ways to do it that I can think of. And let's see if there's anything else I want to cover. I think that's it. I'll make a new video soon about quantum mechanical relativity and explain it a little better for people who are interested. Now, another thing I want to go over real quick is the direct relation of these three energies. If you watched other videos, you'll know what I'm talking about. With electricity, electromagnetism, and magnetism. Now, gravitational energy being equal to mass times the speed of rotation is directly related to magnetic energy. So it's relative to magnetic energy in the universe. So the core of the Earth, if you think about that, the magnetic energy is really created by the rotation and the electrically charged matter, we think. So binary relativity is directly related to magnetism in outer space. And if you don't have rotation, then you don't have a magnetic field for the Earth, which basically protects us from being bombarded by radiation and cosmic rays also from outer space. So we definitely need that and want to understand that. Now, you can prove that there's a direct relation in these two forms of energy because if you can experimentally verify it. There's been experiments where they rotate electrically charged matter and see that it creates a magnetic field. And if you eliminate the rotation, then you don't have a magnetic field. And my theory, which we can prove, is that the higher the speed of rotation, the more energy, magnetic energy, you'll have also, and the more amount of mass of electrically charged matter. So binary relativity is directly related to magnetic energies also out in the universe. Alright, that covers most I want to talk about. And remember, explore your world, explore your universe, and explore yourself. Alright, have a good day.